All right, in 3.8, we're going to talk about our last section of Chapter 8, which is inference for experiments. And it's how do you set up your experiment correctly, and then how do you draw conclusions from it, as significant or not. All right, so first, in the previous two lessons, you learned how to properly design an experiment. We talked about random assignment, we talked about having control and blinding and things of that nature. In this lesson, you will learn how to outline a completely randomized experiment, how to analyze the results of an experiment that compares two treatments. In a completely randomized design, the experimental units are assigned to the treatments completely by chance. You would use one of the methods that we talked about previously, slips of paper, random number generator, any random method to assign them treatments. So here's an example. This guy's class had 20 students, and they wanted to compare the difference between drinking caffeine and no caffeine on a change in your pulse rates. All right. So notice that there are 20 volunteers. You start with however many subjects you have. Basically, it's really easy. 20 volunteers. Then you also always have this section right here, random assignment, into the two groups, and then you state how many are in each group. Group 1, Group 2, so we split it evenly in this case, 10 and 10. Treatment 1, Treatment 2, and then you identify what is the treatment. This group got caffeine, this one had no caffeine. And then you draw arrows to the main idea. What is it we're measuring? We are comparing the change in pulse rates. Okay, you could be measuring biomass, you could be measuring all kinds of things, but you got to tell me what it is you're measuring. This is the response variable right here. That always goes at the end, okay? So random assignment to treatments is absolutely essential in any experiment. And there is no requirement that treatment groups be exactly the same size, although there are some statistical advantages if they're roughly equal. You want to try to keep them equal if you can, but if it's an odd number of people, you can't. So do your best with that, all right? So before making any conclusions, we must account for possible differences in response that could occur due only to random assignment of treatments. That is, we have to make sure that the difference in response for the groups in an experiment is larger than what we would expect to occur simply due by chance variation in the random assignment. If this is true, if it's bigger than what we think would happen by random, then we call those results statistically significant. This is a big concept. Make sure you write this down. When an observed difference in responses between the groups in an experiment is too large to be explained by a chance variation in the random assignment, we say the result is statistically significant. Okay? So another way you can think about this, if you'd rather have numbers, it's considered statistically significant if it happens less than 5% of the time. We consider that statistically significant. Okay? If it happens more than that, then it could happen all the time. We don't really know. But if it happens less than 5%, less than or equal to 5%, 5% of the time, that is if you need a number boundary, that's what determines statistically significant. So let's look at this experiment again. One of the most popular web-based long-distance services is Skype. How will the appearance of ads during calls affect the use of the service? Researchers design an experiment to find out. They recruit 300 people who have not used Skype before to participate. Some people get a version of Skype with no ads. Others see ads whenever they make calls. The researchers are interested in frequency and length of phone calls. Outline a completely randomized design for this experiment. Right? Notice it says outline. That is your clue. You're going to be drawing a diagram. Okay? So start with however many people they gave you. They gave us, what, 300 people. Okay? So we're going to start with 300 volunteers. Now, with those 300 volunteers, we have to do random assignment. That's always going to be your second step in any experiment you design. Always there. Now, what are we randomly assigning them to? Well, to two groups, right? Group 1. That would be half of them, so 150 volunteers. Group 2, that's the other 150 volunteers. And what is Group 1 getting? They are going to get the ads with Skype, and the Group 2 is without ads. All right? And then what is it that we're comparing? Okay, notice what it say, the frequency and length of phone calls. So that's what goes over here. Compare. So make sure you give yourself space on your paper to diagram this. Make sure you label it carefully, group 1, group 2, how many are in each group, what is the treatment to each group, and what is it that you're looking at the end? What are we comparing? Don't forget always to do that random assignment as your second step.
Okay, sometimes when you do an experiment or you're designing one, sometimes it just makes more sense to do what we call blocking it. A block is a group of experimental units that are known before the experiment to be similar in some way, which is expected to affect the response to treatments. For instance, if you know gender may affect the outcome, you may want to block by male and female. Or if you know there's some characteristic that you could break the subjects up by that would make a difference in the outcome, then that would be wise to block. So why do we block? Well, when blocks are formed wisely, it's easier to find convincing evidence that one treatment is more effective than the other. Because you've taken out one variable in one way or another, like you took out gender or whatever you think might be influencing the outcome, you can block it by that. So let me show you an example. A mobile phone company is considering two different keyboard designs, A and B, for its new smartphone. The company decides to perform an experiment to compare the two keyboards using a group of 10 volunteers, 4 of which currently use a smartphone. The 10 volunteers will be divided into two groups of 5, with one group assigned to keyboard A and the other assigned to keyboard B. The response variable will be typing speed measured in words per minute. So it really doesn't make sense to divide them into 5 and 5 because some people use smartphones and are used to the keyboards and some people don't. Now, this isn't true now in this day and age, but that used to be true. So it makes more sense to block by whether you use the smartphone or not. So we're going to start by this block. We split them up by what we think could affect the outcome. And it doesn't necessarily mean that it has to go 5 and 5. In this case, there were only 4 smartphone users and 6 non-smartphone users. Now from here, we have to assign the treatments, and we have to have that random assignment aspect that we've talked about before right here. We put that random assignment. And then we split them into keyboard A, keyboard B, keyboard A, keyboard B. And again, the response variable has to be clear. We compare the typing speeds of each, and then you combine the adjusted results and compare, because now we can clearly see if there really was a difference, taking out the fact they did or did not find a smartphone convenient or familiar. All right, so this is why we block. Now, this is the end of the video. We will do another example of blocking in class, but hopefully this will make sense to you. When it makes sense to group them originally before you randomly assign treatments, that is what we call blocking. And again, it helps us to make more clear the evidence that we get from the result.